we cover some just guided system design and analysis, and also we will study about the target state model. Okay, so as we have discussed this figure, the random error this figure gives you the seeker block diagram without the random error. You know what is the random effect? This is seeker axis, and this is a dish antenna, and here is a target. Okay, and this is the radar. So we consider, suppose there is no random effect. So for example, the random effect is ignored. Okay, so this figure illustrates the kinematic tracking loop of simple propulsion navigation guidance system. They describe dish dynamics in the absence of radar random effect and having the seeker bandwidth. This is a seeker bandwidth omega s. So we keep the seeker bandwidth equals to time constant. This is Ts, the time constant. So in this case, without the random effect, we want small time constant, because in order to make the dish antenna equals to line of sight rate, means this dish antenna equals to the line of sight range, like this one. Here is the angle of gimbal angle, and this is the seeker body angle or axis. Okay, and this is apparent target. So with radar effect, the radar antenna direct to the apparent target. This is the radar effect. Okay, but we are only considering without the random effect, so there is no. Okay, so this there is also angle of dish antenna. Okay, dish angle. So without random effect, we want to make the dish antenna rate of the dish antenna angle equals to the line of sight, so that we can track the range. Okay, so that we can track the range. Okay, so range can be tracked if equals to the line of sight angle, right? Okay, this is the line of sight angle, right? And this is the dish angle, right? So if we make the time constant small, if we make the time constant of the seeker distract, then the seeker distract and the line of sight will be approximately equal. So you have to make sure the time constant is adequately small, capable of tracking a highly maneuvering target. And you have to keep in mind that the increased miss distance associated with the radar guided air defense missile can be blamed on random reflection error. So if there is a random reflection error, then we can increase the number of miss distance. So, and here we can see that our epsilon perfect, what is epsilon? Epsilon is the error, random error. So if this antenna equals to line of sight right angle, then E perfect is equals to this one. So we want this approximately equals to 0. So there should not any without small negligible error is going to track the range. Okay, so here the true rate of angle of the range and the dish antenna rate. Okay, so this must be okay.
Yep.
So in the above figure, the geometric tracking error without the random error is this one, where the sigma d denotes the seeker angle dish. Now the radar converts this error into voltage, which is then filtered. This is done in order to achieve the proper driving signal that will process the seeker antenna in the direction that acts to reduce the error, random error perfect to 0, so that we can directly track the range in this target direction. Okay, and then the seeker angle and the line of sight angle are equal in the case the seeker tracks the target precisely. This is only done when epsilon perfect to 0 or approximately 0. Okay. As in the previous lecture, as I told you, the FCS, the flight control system, control the seeker central line position according to the target line of sight, because the gimbal that is holding the antenna is movable. We can move the computer, move the antenna with the help of gimbal according to the line of sight. Right? So the seeker center line is a seeker center line or seeker axis is controlled by some computer or FCS control system, and is periodically updated based on the reconstructed line of sight angle. So to make sure that this antenna is focusing on the target. Okay. Okay, suppose we are discussing about the guidance filtering. This is a simple diagram. As we discussed previously, our propulsion navigation system in figure number 15A. This is this tube diagram is without radar effect. There is no radar effect, and this figure consider the radar effect. Okay, although the this perceived diameter is all same, the simplified particular dynamics is used for the propulsion navigation. Okay, so the guidance computer formula are same and FCS is same. Okay, at the here the line of sight true angle, okay, line of sight true angle and guidance sensor, without random defect. The guidance sensor receive the true angle and total line of sight angle noise. We will write the equation for the noise angle in this lecture in the next slide. So this is the total noise entering in the system and the true angle. So our line of sight angle is corrected with the line of sight angle noise. Okay, then this interangular system. Now without random defect, our delta D is equal to the delta of the line of sight angle, because here we want to make we consider the small time constant of the dish antenna, dish range, so that our dish focus only towards the line of sight angle. Okay, so here equals, and there this is the guidance formula for the propulsion navigation system, and this is the flight control system transfer function, which will give you the acceleration of the missile with respect to the y altitude. And similarly, this is if we put the feedback transfer function to make the dish antenna, here we can check the random effect error like this one, so that we can minimize the error, the epsilon error. Okay, with the help of the small time constant, to make the dish antenna equals the delta dish antenna equals to the rate of the line of sight, and this guidance system and the FC system. And similarly, this is without random effect. And if you consider the random effect, then there are many things involved in this figure. As we can see that here lot of input which are noise input. Okay, for example gimbal angle. Okay, and the start from here it will give you the acceleration of the missile, and this is the flight angle, rate of flight angle of the missile, and then FCS control system will give you control information, control surface information, for example aerodynamic information and aerodynamic drag coefficients. Okay, and also pitch angle. What is the pitch angle from the with respect to the aerodynamic here, and then it integrate the pitch angle to give the theta is also entered here, and the gimbal angle, and this is the R is the slope of the error. This is the error. So this is the R. R is the slope of the error, and there is a random angle. Okay, and here is total angle angle noise and the true angle. So, and here same thing, if we make the delta D in the feedback to make the error is 0. So here also when sigma true is filtered out like sigma, then it will comes like epsilon sigma minus sigma d. Okay. So here in this diagram, at this section, sigma true it has angle of r, the right arm angle right and error slope, and then angle of gimbal here and here, this angle. Okay, so so pitch angle it's come from the FCS. So this crack loop will minimize the error and with the help of this transfer function, and this will gives you the approximately equal to the at this output with the help of time constant will give you angle of this antenna will approximately equal to this is dish and this is line of sight angle. So to make the dish antenna approximately equals to the line of sight angle, we make the feedback like this one. So this is the correct loop. Okay, clear? And this is the same thing, just we modify a little bit this figure. There is nothing different between them. Okay, understand, clear?
Professor,
Yeah.
I want to confirm my idea to you. The 4 category control loop exists for same purpose to represent the formula, error formula. But I want to can you write a keyword each other the loop? I want to separate the loop.
That's why I've separated this like this one. And we have already discussed the errors and angles, because there are many errors like random error. So this is not error, this is the angle of random effect. Okay, like this one. This is angle of random error. And what is the angle of random error? This is the angle between the apparent target and the true target. Okay, this occurs due to the reflection of the, because when RF signal passes through the radome, it's reflected like this one. It is reflected to another direction. Although target is here, but it's reflected here. Okay?
Yeah.
So, and here, this is affected by, and this is depend on gimbal angle, this angle. Okay, because suppose this antenna is held by some gimbal. This is the gimbal. Okay, but the gimbal is positioned like this one, and antenna position is like this one.
Yeah.
So if this is at this position, then due to refraction, the signal goes upward here. So our FCS control system monitor the center axis of the seeker to reconstruct the line of sight angle by moving the gimbal angle here and here, so that it makes the exact line of sight range here. So without considering the random effect, our guidance system is very simple. It's very simple. The line of sight angle, right?
Yeah.
This is true, which is corrected by the total angle noise here. So by considering the small time constant, we can make the this antenna approximately equal to the line of sight angle, because here there is no random effect. But with the random effect, there are many things, because angle of the radar is depend on the gimbal. So this is also included in this block diagram. So that we have this angle, and then pitch angle. Pitch angles come from the FCS. FCS, the aerodynamics.
Yeah.
Okay. Pitch angle is this one. Seeker body axis to the line of sight. Our aircraft body is moved like this in this direction. The seeker body axis. So angle between the seeker body axis is our pitch angle. This pitch angle. So the aircraft is moving this direction. So FCS receives the control surface information, and the control surface information. There are many coefficients, dragging coefficients, which make the pressure wind, or which force the aircraft. Which there are many forces outside the wind.
Yeah.
Okay. So this pitch angle is received by here. This which is indicated with to give here theta. So we have to consider the geometric effect or geometry or projectile of this variable, and this variable, and also the this antenna variable. Okay.
Yeah.
Clear now?
Yeah, clear.
Okay, are you clear?
Yeah.
Now, this figure B, if you remember the figure 2.2 earlier when we start the chapter, consider the block diagram corresponding to figure 25, figure 2.15b, the trajectory dynamic model. Now target position measurement is this one, z equals to yt and yg. Yt is the target maneuver or target state or target measurement. This is the error or noise. Yg is a target glint or scintillation noise. Scintillation is the radar return signal, or glint means spark. Or this comes from the return signal. Suppose this is the target moving towards this direction, x direction, and here is the engine. So engine emits some energy from the engine, in shape of some spark, in shape of some energy signal or gas signal, like this one. So when radar receive the signal, return signal from here, then this is like here. And great noise is this is return signal. Great noise is great noise is the variation of the amplitude of the return signal. We can see the return signal have some variation of the amplitude up and down. This is called glint noise. So glint means noise, that noise which is continuously variable, continuously varying the amplitude of the signal. So this target glint noise is generated by the target engine or engine energy or some like thing like this, or fuel energy, okay, fuel or thermal. Okay, so and we YT is the target position. Now this is the angle tracker noise. Angle tracker noise, as we discussed at the start of the chapter, the angle tracker noise is included thermal noise, padding noise, and collector noise. Okay, and this also the target thermal noise, padding noise, and collector noise. This all enter into the system, and this is the range between the target and the missile, and the target position. And this is the target noise YG, and this gives you the Z. So Z complement means the Z is the vector, column vector, and here Y, and here this gives you the position. When we double integrate the acceleration, this will give you position, and here we can get the error between, or difference between the YM and the target position. So this is the simplified model. Now we have to study about the noise, because when we start about the estimation, we have to consider the noise and noise covariance, variances. So now this is all about the noises, and the two noises, one is the YG and other is the angle tracker noise. Okay, these noises which corrupt the observation, induce misdistance, and impact perceptual acceleration requirement are assumed to be uncorrelated white process noise. So represented as a linear displacement at the target YG is a forward spectral density of psi g. So we assume all noise is a white noise. So suppose number one, two noises. Number one is a glint noise of target. Okay. So glint noise is represented by YG as a power density spectrum of psi g. Okay. Now, like a misdistance, this psi g is the power density spectrum is divided by the range to become an angular glint noise. This is the power density spectrum of a glint angular This is the angular glint noise has the power density of this one. This is the angular glint noise. This is angular glint noise has a power density spectrum of this equation phi d over r square. Okay. Target scintillation is commonly assumed to be structuring band limited noise, the amplitude and bandwidth being function of physical dimension and motion of the target. Means this has a bandwidth and the amplitude physically equal to the dimension and motion of the target. Because this the engine generate a lot of energy. The amplitude and the bandwidth of this energy of the target is equal to the physical dimension and motion of the target. As long as the target moves, the energy continuously exhausted. And other noise is glint noise. Target glint noise continues. The simulation can be performed by introducing the simple leg filter. This is glint less leg tracker. Okay, with the time constant. This is the time constant of glint leg tracker 1 upon omega g. This time constant is between the omega g and yg. Yg and yg. This is the bandwidth, and this is the noise, glint noise. Okay, this is the glint noise. This is the angular glint noise. Okay, so time constant between the bandwidth and the noise of the glint is given by this equation. So what this is 2b so now what is the power density spectrum of this one? The power density VSD of the YG is 2 tau GLT or GLT. So this is the variance. Okay, this is the variance of the grain noise. So when you go back to the first lecture of this chapter, you can see the leg noise leg filter. But this leg filter we have discussed in figure 2.2. But for simplicity, we have removed the leg filter because it falls outside the homing loop. Okay. Now all noises are Gaussian process. Okay. So the return signal, that is the YG or glint noise, is also normalized with a Gaussian white noise with a zero mean and variance GLT. Now this is again variance is this variance determined by the target wing length Ws divided by A. And A is the thumb rule and can be varied between the 2 and F according to the data. So the variance of the glint is coming from the engine. The glint noise is inside the energy signal. Okay, suppose this is a energy signal, but here some variation due to the glint noise. Okay, here some variation due to the glint noise, and this glint variation, glint noise Yg has a variance equal to this one and determined by the target glint length and the thumb rule. Okay. Now angle tracker. This is a now in this case we have three noises. Sigma f is also Gaussian normalized with zero mean and variance Rf. Okay, with PSD, white noise PSD. RIN is a range independent noise. This is range independent noise. This is the range dependent noise. Means it depends on the range. The thermal noise depends on the range, and this is range independent noise, fading noise. And as a power density spectrum, PSD is 2. So again here tau f is the time constant of the fading signal and the variance of the fading. Of the fading noise. Now this is the receiver noise. Okay, this is the receiver noise, and it is caused by many sources: signal processing effect, cross polarization of the data returns, quantization effect, gimbal servo drive inaccuracies, and thermal noise is also a receiver noise, which is a function of target. Function is target signal, return signal strength, and the signal to noise ratio. So thermal noise is also has a zero mean and variance Rn with PSD. So this is time constant, and this is the variance of the thermal noise angle. Okay, and now third one is the collector. Collector is also white Gaussian normalized with zero mean and variance RC with PSD. Okay, here also in the same way, tau C is the time constant of the collector noise, and the RC is the variance of the collector noise. Now, the glint noise, receiver noise, and RIN are important contribution to the tracking accuracy. Okay. So decreasing the range means if the missile and the target are very close, decreasing the range to go increasing blink noise. If the missile and target is very close, the glint is more. The frequency increases. Frequency of the glint increase, but it can decrease the thermal noise or receiver noise. But if the range is far, the glint noise decreases. If target is far, then there is a glint noise very rare, very small. Now the variance RTN and spectral density of the rectangle transfer, because this has a variance RTN and PSD psi TN. Now this is the sum of the all variance of the noises. Okay, the variance of anti-tracker noise equals to the Rm plus Rf plus Rc. Okay, and similarly this is equals to the all power density, summation of all power density, like this one. Okay. Now total angle noise, total line of sight angle measurement noise becomes the sum of this. Okay. So if we sum up the all noise, we get the total noise, like this one. Okay. Now this has a variance of this one and the PSD this one. So this is the variance of the this one and PSD. Okay, this is the variance and this is a power density spectra. Now what is the variance? This is equals to the variance of all measurements, all noises, for example Rm, Rf, and Rc, and this is a glint variance. This is the variance of the glint noise, and this is depend on the range R, and similarly this is sigma all power density spectral Okay, so now finally we can add all noise with the target. So here n is the sum of grid noise and the angle track noise. Okay, but angle track noise is multiplied with the R. So n is, we can write n like this one, V sigma into R. Okay, so our total noise, where we have added the track noise and the YG, so the target position is now becomes like this one, Z is equals to YP plus N, and N is this noise and R. So we can write this equation like this one. This R is multiplied to only this one, not at this. Okay. Because here this angle, this is separate from this one. Okay, so this is equals to the R times, okay, this is R times multiplied and added with this noise. Okay, now this target position noise has a variance and the PSP. Variance has a RN and PSP phi n. Now if we look over this one, this is equals to R square sigma. If we do some solution to this equation, and RF or RC R square and plus R G and T. So therefore our Rn is actually R square and sigma. Our Rn is actually this one. So we can write this equation like this one: Rn plus Rn plus Rc RGLT. So this is the variance of the noise, and similarly we can make change to this equation like this one: M plus F plus collector R square plus 5G. So this is the final equation, which have this is the variance and the power density spectrum of the target noise. Now our block diagram of 15B is simplified to become like this one. We have a noise is VR. This is not actually V, this is some different notation. This is like this notation. Okay. V V sigma R noise and Vt. Okay, so this has all noise, the glint noise and the angle bracket noise, all noise included here, and target. So target is corrupted with all noises and will give you the Z measurement. So our Z measurement is a corrupted data, and this is the guidance system, and which gives you the position of the missile. Okay. So other than that, other noise, there are non-noise input. We can, such as the initial condition noise or something like this. Initial condition at the start of forming is a non-noise input. We can make it to 0 or constant, or initial seeker error or initial turning rate of the missile are both assumed to be constant random variables. For example, either of these two may be 0. For example, the seeker initial error input becomes 0 if the seeker is locked on. If the seeker is locked on or settled out at the start of forming. And similarly, initial running rate input becomes 0 if the missile is not maneuvering when forming begins. Okay, so basically this is our GNC system, and figure 15C. The dotted box is a guidance filter. Now the pursuit lateral position output by M, this is controlled by the guidance computer. And this is controlled by the guidance computer or XCS. To minimize the covariance of the pursuer to missile, that is minimum missed distance. The guidance and control system must get the missile close enough to kill the target when the ball will explode. Therefore, appropriate measure of guidance performance is missed distance, which is defined as minimum distance between the missile and the target. So therefore, we need to design a compensation guidance filter that must be used to maximize the range of operating condition, allowable environmental noises, reliability and effectiveness. So here is some design requirement and consideration. And all middle of the blocks are the closed loop. First one is the model development, which include the wind tunnel test, CFD, CSM. CFD is a computational fluid dynamics. CSM is command and service model. Physical laws and system identification, model validation. This is model development parameters, and this is a design specification. What are the military specification, flying qualities, stability requirement, missed distance, performance. These all model development and design specification will undergo open loop analysis. In open loop analysis, we use the root locus to check the stability, covariance, observability, controllability, and then we use the frequency analysis to analyze the missed distance parameter. Okay, this is open loop system, and the results are used to define the design model. Now, this block diagram is a control system diagram, which is actually computer-aided control system design, which use 3 controller, feed-forward controller design to enhance the command response, feedback control design to satisfy the stability and robustness requirement, and controller order reduction to minimize the implement complexity. So here we apply advanced guidance and control laws, or we apply we follow guidance law in this block diagram. Okay. Now this is again feedback or closed loop to back to the design specification, because until the closed loop system satisfies the system specification, it will go back and again analysis and then go back, then again analysis and come here, and also model development and then simulation performance evaluation. It conducts a closed loop analysis which combines control system design and open loop simulation model. This is done to ensure that a control law design satisfies the control functional requirements. So here, time and frequency responses, linear, nonlinear simulation, repetitiveness, margin assessment, and then finally we have a hardware and loop simulation, where we will finally build up a fast prototype and environmental test. Okay. Now, earlier they use classical control system for generating the acceleration command. This is line of sight, right, and plus some noise signal which is passed through the low pass filter, which gives you the filtered line of sight, right, and which is applied to the guidance proportional navigation guidance law to give an acceleration command. Now modern system uses the optimal filter estimator like gamma filter to filter out the line of sight, right, and gives you the good amount of the signal compared to the classical signal, which is applied to the advanced guidance law, which gives you better acceleration command. So this is the block diagram comparison between the classical, which use the low pass filter, and the modern approach, which use the optimal estimator. Almost the blocks are similar, just looping and estimator. We use the here estimator and advanced optimal guidance law. And this is simple. Earlier they used the proportional navigation law. This proportional navigation law is used for tracking the non-maneuvering target. But advanced, we can track the maneuvering target as well using the advanced guidance law and estimator. So in the modern approach, the dynamic sensor also estimated with the optimal estimator, which again feedback to the optimal guidance. Okay. Now stability. Consider the simple block diagram of the Percival dynamics. As we know, the transfer function is given by this figure. Transfer function of this system is AMI divided by this one. From sigma 2 to AMI is from the figure. The stability and analysis pertains only to guidance system transfer function using root locus, and this analysis will apply to the entire moving loop in this figure using the frequency response analysis. And the moving loop in this figure can be used to obtain a clear understanding of the requirement of the analysis model. Such information is then used to evaluate the effect of the GNC parameter on missile performance. Now our performance parameter are the navigation ratio, guidance system time constant, and effective guidance system time constant due to radar effect. These are our parameters to check the performance of the system. One is the navigation ratio, and this is the guidance time constant, and this is effective guidance, which is affected by the gimbal, okay, or random effect. So important parameter is the time constant of the random effect, gimbal, and the navigation ratio. Okay, up to now, here any question?
No.
And this is just only 5 slides remaining the target state model.
Yeah.
So you know this equation, the nonlinear equation that we have studied in the first lecture of this chapter. So we consider 2 dimensional target tracking problem illustrated in figure 2.10. Okay, for simplicity, let the velocity, target velocity be in x direction while Vm is 0 and gamma is 0 for fixed tracking station. Okay. Suppose in figure 10 where we discuss all angles. Okay. In figure number 10 we have discussed all angle equation and variable and nomenclature. Here in this figure the seeker station is fixed on the earth. So Vm is 0 consider and gamma is 0, and from equation A, B, this is already we have discussed in the first lecture. If we put the Vm 0 and gamma 0, we comes this one. R dot equals to Vt cos sigma, sigma dot equals to Vt R sin sigma. Now differentiate this equation and this equation. This is the U to V formula, and this is the differentiate of U upon V. This one. Okay. Now assume that target is not accelerating. So the Vt dot is 0. Then assuming that a very small change in R and sigma during each 1 to 10 second radar scan. So that R double dot and sigma double dot approximately equal to 0. In this equation, if R and sigma is very small, approximately negligible, this is negligible, and also Vt dot is 0, then this and this will approximately 0. But other than this, there are some other random process noise acting on the target model. Random instruments omega R and omega sigma are introduced to account for small changes in R dot and sigma dot during the each scan time. Okay. So we are talking about the range only. This is range and this is the angle of range, angle of line of sight. So if we add some process noise, then this will comes to omega R. This will come to this one. We have this and this are the process noise, maneuver process noise. Now, because the Kalman filter is robust in presence of process noise, so R dot and sigma dot can be tracked with the help of Kalman filter under the process noise. So thus R dot is equal to R dot, sigma dot equals to sigma dot, and from equation number 3, the linear equation line of sight range becomes 4. This was nonlinear equation. We have differentiated, then make some assumption and adding some disturbance. Now linear equation becomes like this one. So R dot equals to R plus 0 R dot equals to R dot, and double derivative of R dot equals to 0, all 0, and this equals to this one. Sigma dot equals to sigma dot and 0. Sigma double dot 0, all 0, and sigma double dot is equals to this one. Now the measurement equation is given by this equation. This is the measurement equation. Measurement matrix we have discussed. Measurement matrix, and this is the step vector, and this is the noise. This is total angle noise. Total angle noise, which is equal to the gain noise and tracker angle noise, all in this VT. Suppose independent disturbance acceleration of driving white noise are uniformly distributed between NT. NT is the magnitude of the step maneuver. Then WR is radial acceleration with variance. This one. So here our target state acceleration is correlated with the white noise acceleration. So WRT, which is the process noise, is suppose this is the radial acceleration. This has a variance of NT square of 3. Okay, we want to actually define the covariance having the variance this one. So in the covariance, the radial acceleration has a variance of this one, okay, and since the omega sigma is an angular acceleration, this is radial acceleration and this is the angular acceleration, then omega r into r is distributed according to the maximum noise PDF. PDF is a probability density function and has variance of this one. So covariance of process noise omega t and minimum noise Vt are given by this one. So our measurement has a covariance this one and variance this one. We have this and this, it denotes the variance of range and azimuth measurement. Okay. And finally, this is our target state, and this is the transition matrix which is multiplied by this one in order to get the next state value of the target, and this is measurement having the process noise this one and this one. Okay?
Yeah.
So from here, tomorrow we discuss about modern filtering techniques like gamma filter,
Yeah.
then prediction and smoothing. Then after that we will go for a moving loop.
Oh, okay.
So tomorrow we have the class at the same time,
Yeah.
10 o'clock.